We have a quick little side note where I really want to talk about how the amplitude depends on the forcing frequency. And what I notice is quite interesting is I feel like maybe I've really been trapped in this section for too long, because what you can notice is I'm not drawing straight anymore. And that actually, like, we got some kind of like sinusoidal motion of these words up here. I've been staring at too many sine waves today. But we're still on the same example problem. In typical differential equation style, same example, takes the entire section, and we still are looking at the general solution that we've done before. So this is where we're at. This is the forced harmonic oscillator with no damping. This was the homogeneous solution, and then we or the natural response, and we also had the forced response, which was 1 over 2 minus omega squared times cosine of omega t. We can use parentheses here if we want to make things a little clearer. And oh wait, I couldn't decide whether that was a t or a plus. I've committed the greatest sin. So what we're going to do is really talk about the amplitude of the forcing function. Sorry, the amplitude of the forced response. The amplitude of the forcing function is very boring. It's just 1. The amplitude of the forced response is much less boring. So we can plot that, no problem. We know what this function looks like. Specifically, all right, let's draw straight lines, shall we? Or at least relatively straight lines. We know that the amplitude of the forced response is just, well, it's going to be the absolute value of this, but basically going to be this. Okay? It's just a reciprocal squared function with a little reflection, shifted over a bit, and the absolute value actually is not going to do that much. That's very interesting, I think. And what it's going to look like is we'll have an asymptote, of course. Where's the asymptote? It's at the square root of 2. Let's label our axes. This is the omega axis, and this is the amplitude axis. We're showing how the amplitude changes at different frequencies. Well, we know what this graph looks like, or if you didn't, you could plot it. It asymptotes, has this vertical asymptote, and then a horizontal asymptote at 0. As omega gets really, really big, right, the amplitude goes to 0. And if the frequency, I mean, omega could be negative, and it's just going to go, it's going to make cosine positive. So it's going to be pretty boring. So this is what we have. Of course, we saw this as well in Desmos. And what we can say for some of this is that if omega is close to the square root of 2, something really happens. But let's actually talk about if omega is not. If omega is very large, and notably very large, really what I care about is that it's far away from the square root of 2. If our forcing frequency, which will always be the same as the frequency of the forced response, if that frequency is very large, then this amplitude is very small. And what that means is that the forcing function has a very little effect. And again, we're not changing the amplitude, we're not changing the size of the forcing function. That's the interesting thing. We're not changing the size of the forcing function at all. We're just looking at how the frequency of that forcing function changes. And if the frequency is very far from the natural frequency, then the amplitude is very small. And again, when I say very large, I mean far from the natural frequency. Okay? If omega is very far from the natural frequency, the amplitude of the forced response is small, because the forcing function is not the same as the forced response. They will have the same frequency and period, but you can very clearly see that they have a different amplitude here. For other forced harmonic oscillators, one will have a phase shift as well. And so that's quite interesting, is that the effect on the solution depends way more on the frequency, what it is relative to the natural frequency. Similarly, if omega is close to the square root of 2, then there is a huge effect on the natural response. And we saw that in Desmos, right? And this is called near resonant forcing. We'll talk about actual resonant forcing in the next video. And again, we did definitely see that. We saw that on Desmos. I'll show that again. We can see that if omega is really small or really big, specifically if omega, all right, actually, let's go back to this is the initial condition of 0. So if omega is really big and you have an initial condition of 0, that means that it's going to take forever for anything interesting to happen. So I'm actually just going to change this constant real quick. We can change it back to -a later. We'll get rid of these guys. Okay, so if omega is really big, you can see that we have really, like, right, if the forcing frequency is so big, if that period is so long, if the period's so short, the frequency is so big, then again, we have really no effect on the initial thing. But if that is very close to our natural frequency, it has a very large effect. Okay. And so that's pretty much all I really wanted to talk about in this video. And in the next video, we will talk more about resonance. What does actual resonant forcing look like? And we'll answer some questions and we'll solve the actual equation. Because if you remember, we only solved this differential equation for omega not equal square root of 2. What does the solution look like when we have actual resonant forcing? Because we can only get near resonant forcing with this equation. What does the actual general solution look like for resonant forcing? We answer that in the next video.